be wondering, why do I have a tennis ball? Because I'm going to throw this guy. And how far, you may ask? I'm going to throw this as far as I possibly can. So I'm going to throw this with all my might. But the question is, and it's the math question, at what angle should I throw it at in order for it to travel the farthest? That's the math question for today.
This Javelin competition, he really is getting confident and hammers that one out. Oh, look at that. That was a sensational throw. That's got to be over the 90-meter mark. Have a look at this. He wallops it. He really is strong.
Let's look at this. Now, this is primarily a question of calculus, of something that we call optimization. But it's also going to involve, like many calculus situations involve, it's also going to involve some pre-cal stuff like parametric functions, trigonometry, vectors, and things of that sort. So let's look at the situation. So here I am. And I throw this ball. And I throw it at an angle. And I throw it with an initial velocity, which I'll call V0. And I'll throw it at an angle, which I'll call theta. Now, when I throw a projectile, which the ball is once I let go of it, into the air, it has two components to its velocity, which are independent of each other. It has a horizontal velocity, which I'll mark as VH, and it has a vertical velocity, which I'll mark as VV. So I would like to write the horizontal velocity and the vertical velocity in terms of V0. So if you notice that this forms a right triangle with theta being located here, that would mean that the horizontal velocity is the adjacent side and the vertical velocity is the opposite side, and V0 is the hypotenuse. So if I want to relate the horizontal velocity to V0, that's relating adjacent to hypotenuse, that's cosine. So I can say that cosine theta is the horizontal velocity divided by the initial velocity. And if I solve this for VH, I can say that VH is the initial velocity times cosine of theta. Similarly, the vertical velocity is opposite. The horizontal velocity, again, is hypotenuse. So if I want to relate the vertical velocity to the initial velocity, I will use sine, and sine theta would be the vertical velocity divided by the initial velocity. And then, of course, if I solve for the vertical velocity, I'll get that the vertical velocity is the initial velocity times the sine of theta. All right, so we need to know these vertical and horizontal components of the velocity, because I'm going to write a parametric function where the parameter is time of two position functions, one given the height at time t and one giving the length at time t, or the horizontal distance at time t. So the height, the function that finds the height, I'll call y of t, and I'm assuming the units for distance in this problem are in meters. So I'm making an assumption that the units in distance for this problem are in meters, which means my vertical position function will be negative 5 t squared plus the vertical velocity, which is v naught sine theta times t, and I'll stop there. Now we could also put the initial height, but again for this problem I'm trying to see what angle I can throw the ball for it to travel the farthest distance, and for that case the initial height has no relevance on that particular case. So whatever angle it takes to throw it the longest, wherever I start from is not going to change that angle. It makes it go the furthest. Alright, so this is a well-known equation in math and science. The negative 5, you may be wondering, it comes from half the acceleration due to gravity on Earth. And so in meters, the acceleration due to gravity is negative 9.81 meters per second squared. For easy mathematics, I rounded that figure to negative 10. And we take half of the negative 10 to get the negative 5 that we have here. For the horizontal position, which I'll call x of t, its position function is the horizontal velocity, which is v naught cosine theta times t. Now the difference you may notice from these two position functions is they give distance, and distance is speed times time. So here's a very simple distance problem: speed times time. The difference in the vertical one is you have this guy here, and the reason being the speed is being affected by the acceleration due to gravity, and that's why we have this negative 5 t squared. So that's the difference from this guy and this guy. Other than this, they're pretty much the same. Alright. So I have two position functions. One which gives me the vertical position, how high it goes, and another which gives me the horizontal position, how far it goes. For this particular scenario, my question is, what angle can I throw it for it to go the furthest? And when I say the furthest, I'm speaking horizontally. So this is the guy that I'm concerned with. So this is the function that I'm mostly concerned with. And so I'm going to do something in calculus called optimization. And I'm going to optimize this x of t function. And this is what we call the primary equation. But the problem, when you want to optimize a function, the only variable you want to have is the variable you're trying to optimize. Here I want to know what measure of theta, what angle would make the ball go the furthest. So I want to optimize theta. In this equation, the way it is now, I actually have two variables. I have theta and I have t. V naught is a constant. So I have theta and I have t. So when that occurs, you want to rewrite your primary equation with just one variable, theta. So I would like to rewrite this equation just in terms of theta without a t. So I want to remove the parameter t. Here's how I'm going to do it. So here is the projectile, the trajectory of this ball I'm throwing. So it's going to go up and eventually going to start going down, and then eventually it's going to hit the ground. When it hits the ground, it will have traveled the full distance. When it hits the ground, it will have traveled the full distance. And it's going to hit the ground at some time t. So I would like to know the value of t at this moment when the projectile hits the ground, because at that value of t, the projectile would have traveled its full distance. And the maximum of this distance is what I'm trying to find. So the good news is the projectile will hit the ground when its vertical position is 0. So the projectile hits the ground when its vertical position is 0. So to find the value of t and where it hits the ground, all I have to do is set my vertical position function equal to 0 and solve. So let's let's do so. So let's set this equal to 0 and let's solve. Now, this may seem like a very difficult problem to solve, but really it's not. So this is a quadratic equation. Again, I'm trying to solve for t here. This is a quadratic equation. So I can solve it. One way I can solve it, there's a couple of different ways I can solve it. One way I can solve it is using the quadratic formula. So I'm going to use the quadratic formula. For those that don't remember, the quadratic formula, in this case I'm solving for t, t would be negative b plus or minus the square root of b squared minus 4ac all divided by 2a. So I'm going to use the quadratic formula to find the value of t where the projectile hits the ground. Now, one thing you have to understand in this problem. So for my scenario, I put that there wasn't an initial height. So when I first throw the ball for my scenario, I'm saying the initial height is 0. So there's actually two values when a projectile is going to hit the ground. Where it starts at time t equals 0 and this guy. So this quadratic equation is going to give me two solutions. One of the solutions is going to be 0. That's not the solution I'm concerned with. The other solution is the solution I'm concerned with. So just bear in mind, based on our scenario with this not having an initial height, that one of the solutions to this is going to be 0, which we're not going to need. It's not going to help us very much. So we're going to discard that particular solution. All right, so for this particular problem, the value of A is negative 5, and the value of B is V naught sine theta, and there's no C, so the value of C is 0. So let's plug this in and solve for t and see what happens. So then t would be negative V naught sine theta plus or minus the square root of V naught sine theta squared minus 4 times A, 4 times negative 5 times C times 0. It just so happens that 4 times negative 5 times 0 is 0. So this part is going to be 0, so there's no need to write it. And all that's over 2a, so all that's over negative 10. So I'm going to go ahead and solve this. Now, you may notice that here I have the square root of V naught sine theta squared. So of course if I take that square root, I'm just going to get V naught sine theta. So I claim that t is negative V naught sine theta plus or minus V naught sine theta all over negative 10. Now you can see from here that if I was to add these two, that would be negative V naught sine theta plus V naught sine theta, that would be 0. That's the solution that I said we're not going to use. So doing the plus part of the plus or minus will give me 0. That's not the answer I want. So the answer I want is going to come from the minus part of the plus or minus. And so negative V naught sine theta minus V naught sine theta is negative 2 V naught sine theta. So t would be negative 2 V naught sine theta over negative 10. And if you were to reduce negative 2 over negative 10, you'll get 1 over 5. So this is V naught sine theta over 5. So the value of t when a projectile hits the ground at the end is calculated by V naught sine theta over 5. Now again, my objective for getting this particular figure is so I can substitute it into the horizontal position function, and where it's no longer in terms of theta and t, it's just in terms of theta. So to remind you, the horizontal position function was this guy. where x of t was v naught cosine theta times t. And so this is what I want to optimize. This guy right here is what I want to optimize. Again, the problem was I have this variable t. Well, here I have t in terms of theta, so I'm going to substitute this value of t into here, and that'll make this function in terms of theta and no longer in terms of theta and t. So I'll call this x of theta now, and this will be v naught cosine theta times v naught sine theta divided by 5. And then we just kind of multiply and simplify a little bit. This will be v naught squared over 5. So I put this in front because these are just constants times cosine theta sine theta. All right. This is what I want to maximize. So, to maximize, to optimize a function, we find its critical points and the endpoints of its implied domain. So let's talk about the implied domain of this particular scenario. So I want to throw the ball at an angle. The lowest I could possibly throw the ball would be at an angle of 0. The biggest angle I could throw the ball would be at an angle of 90. So the implied domain is 0 to 90. So my implied domain is that theta is between 0 and 90 degrees, or 0 and pi over 2 radians. So what I'm going to do is I'm going to take the derivative of this and set it equal to 0. That's going to find my critical point or points. And then when I find my critical point or points, I'm going to plug them and the endpoints of my implied domain into this function. And the one that gives me the biggest value is what we call the maximum. And it will be the one that will make the ball travel the furthest. So let's take this derivative. So if I take this derivative, and again, v naught squared over 5 is just a constant. In fact, I could really do this problem with disregarding the v naught squared of 5, because whatever is going to make this the biggest, that value times v naught squared of 5 is going to be, it's not going to change anything, because v naught squared over 5 is going to be a positive number. So really I can do the problem disregarding the v naught squared over 5, but I'll keep it there for now. So this problem is going to require the product rule, and so I'll take v naught squared 5 cosine theta times the derivative of sine theta, which is cosine theta, plus, I'm not writing a plus because I understand I'm going to have to take the derivative of cosine, so plus v naught squared theta, and now I'll take the derivative of cosine theta, which is negative sine theta, so then minus v naught squared theta over 5 sine theta times sine theta. So the derivative seems to be, in my humble opinion, the derivative seems to be v naught squared over 5 cosine squared theta minus v naught squared over 5 sine squared theta. So to find my critical points, I just need to set this equal to 0 and solve for theta. So let's do so. So we're going to set this equal to 0. And again, you'll see another reason why I could have really just disregarded the v naught squared over 5. So I want to set this equal to 0. I have these two coefficients. It makes sense to divide everything by this number. So I'm dividing everything by v naught squared over 5. And I get cosine squared theta minus sine squared theta equals 0. So I need an angle between 0 and 90, or 0 and pi over 2 radian, where cosine squared theta minus sine squared theta is 0. Now one way you can think of it, for cosine squared minus sine squared to be 0, that means that cosine theta should equal sine theta. Now technically, because it's squared, you can say cosine theta can equal plus or minus sine theta. But since we're in quadrant 1, since our angle is going from 0 to 90 degrees, then it just means that cosine theta should equal sine theta. Now your understanding of trigonometry, you should already know what that angle is. But I'm going to work it out a different way. So you may already know what angle where sine and cosine are both the same. But I'm going to work it out in a different way anyway. So let's say I rewrite cosine theta using one of our Pythagorean identities as 1 minus sine squared theta. So let's say I rewrite this as 1 minus sine squared theta minus sine squared theta equals 0. And so that's 1 minus 2 sine squared theta equals 0, which means 2 sine squared theta equals 1, which means sine squared theta equals 1/2, which means sine theta, equals the square root of 1/2. Which is 1 over the square root of 2, or it can also be thought of as the square root of 2 over 2, and the value of theta between 0 and 90 that satisfies that this particular value is 45 degrees, or pi over 4 radian. And again, that's the same value that where sine and cosine of theta are the same. Sine and cosine of 45 degrees, or pi over 4 radian, is the square root of 2 over 2. Alright, so this is my one critical point where theta is 45. The endpoints are 0 and 90. I'm going to plug those into my primary equation, where it was x in terms of theta, and see which one gives me the biggest value. So that primary equation was x of theta was v naught squared over 5 cosine squared cosine theta cosine theta sine theta. Alright, so let's plug in the values. So if I plug in 0 for theta, well, I have to take the sine of 0. The sine of 0 is 0, so all of this is going to become 0. Cosine of 0 is 1, but the sine of 0 is 0, so this would be 0. Let's try the other endpoint, 90. If I find x of 90 degrees, well, the cosine of 90 is 0. Sine of 90 is 1, but it doesn't matter. Cosine of 90 is 0, so all this will be 0, and so I get 0. Now, if I plug in 45, cosine of 45 is 1 over the square root of 2. The sine of 45 is 1 over the square root of 2. And 1 over the square root of 2 times 1 over the square root of 2 is 1/2. So I know I have this v naught squared over 5, but it's being multiplied by 1/2. And so this is some positive number times 1/2. That's going to give me a number that's greater than 0. So I feel like we have come to the conclusion that if I want to throw a ball and have it travel the furthest distance possible, I should throw the ball at an angle of 45 degrees. But I want to go one more step to confirm that this is indeed the true answer. My implied domain didn't give me a whole lot in this situation. In many situations it doesn't. In many situations, but not all, but in many situations, the real answer comes from the critical point. But perhaps I messed up on my implied domain, and I want to ensure myself that this critical point represents a maximum and not a minimum. So to just confirm, I can do the second derivative test. So I'm going to do the second derivative test. I'm just trying to make sure that this indeed is the correct answer. So if you look at a graph, so here's a graph that's concave up, and this would be called a relative mean. Here's a graph that's concave down, and this will be called a relative max. So what you notice for relative extrema, when you have a relative max, the graph is concave down close to that point. So what that means when a graph is concave down, that means the second derivative is less than 0. And when you have a relative min, the graph is concave up, which means the second derivative is greater than 0. So I can find the second derivative of x and plug in 45. If I get a negative number, that confirms that 45 was a max. If I get a positive number, that's telling me that 45 is actually a relative min, and I got to go back to the drawing board. So let's see what happens. All right, so when we did the first derivative, I'm about to do v prime, not sure what I'm thinking about velocity. The first derivative was v naught over 5 cosine squared theta minus v naught squared over 5 sine squared theta. So then the second derivative and notice when we did the first derivative we had to do product rule. Now in the second derivative we don't have to do product rule anymore, so we should be a little excited. However, we do have to do some simple chain rule on this problem. So what's going to happen here is the derivative of cosine squared. I'll get a 2 cosine theta and then times the derivative of cosine, which is negative sine. So that will be negative 2 v naught squared over 5 cosine theta sine theta. And next, when I take the derivative of sine squared theta, I'll get a 2 sine theta times the derivative of sine, which is cosine. So that will be 2 sine theta cosine theta. So minus 2 v naught squared over 5 sine theta cosine theta. Well, I said sine theta cosine theta, but why not write it in an order consistent with this? So cosine theta sine theta. So these are the exact same terms. There's a minus sign in front of this. So if I combine those, that'll be negative 4 v naught squared over 5 cosine theta sine theta. And now I just need to plug in 45. Again, if I plug in 45 here and I get a negative number, that confirms it's a max. So that's the answer. If I get a positive number, I got to go back to the drawing board. So let's see what happens. So I'm plugging in 45. Double prime, please forgive me, x double prime of 45 degrees. Alright, so the only calculation is here. And again, this is 1 over the square root of 2 times 1 over the square root of 2, or the square root of 2 over 2 times the square root of 2 over 2. However you want to think about it, you're going to get 1/2. You're going to get positive 1/2. So you're going to have negative 4 v naught squared over 5 times positive 1/2. This is a positive number and this is a negative number. Again, v naught squared is going to be positive. So, but it's being multiplied by negative 4. So this number is negative and this number is positive. So their product is negative. So that means that the second derivative is less than 0, which confirms that theta equaling 45 is a relative max, which means that the angle that I can use to throw the ball the farthest is 45 degrees.